Okay, welcome to a video I thought I'd make on complex integration. Um, there's been two major theorems that you've learned recently in complex analysis. One of them is Cauchy's integral theorem, and the other one is Cauchy's integral formula. We didn't really get a chance to speak much about Cauchy's integral theorem in tutorials. There weren't really any questions on it. And also, Cauchy's integral formula, we won't be having a tutorial in week 8 because you have your mid-semester test. So we won't really have a chance to talk about Cauchy's integral formula in tutorials either. So I thought I'd make a video explaining these two important results, and hopefully after this you should find the questions in the practice the problems in the practice test which G put up, you should find them quite easy, and you should find the assignment fairly routine as well. So before I get to those two results, let me just give a quick review of what we've learned so far when it comes to complex integration. So far we've talked about two different techniques when it comes to integration. Now both techniques require f to be continuous on C. So maybe let me write it like this. So suppose you have the complex plane and you have some point Z1 and some point Z2, and you have some contour, some path going from Z1 to Z1 to Z2, and I'll call this path as C, or this arc C. And what we want to do, we want to integrate a function f of z dz along C. So far we've talked about two different techniques to do this. Both techniques require your function f to be continuous on C. Okay, so the first technique which we spoke about was using what's called the fundamental theorem. Okay, what this one says, it says that if f has an antiderivative, I'll call big F, which is analytic in a domain D containing C. So what does that mean? It means, let's say, for instance, you can draw some domain D which contains C, and let's say this antiderivative big F is analytic in that domain. In that case, we can apply the fundamental theorem, which tells us that the integral of f of z along C is equal to, well, it's just like what you learned in first year. So you compute the antiderivative capital F at the endpoints and subtract. So this is a very nice result, very nice in the sense that it resembles what we learned in first year, and if you can use this fundamental theorem, then of course you go ahead and use it. But sometimes you get a function where it may not have an antiderivative, or maybe its antiderivative is hard to calculate. In that case, you can use a second technique. You can use parametrization. So in parametrization, we basically just have the following formula. Integral of f of z dz along c is equal to the integral from b to a f of phi of t times the derivative of phi dt, where phi is some parametrization of c. So where psi of t going between a and b, is a parametrization of c. So those are the two techniques which we've spoken about so far. The next technique, or the next result, which we're going to speak about first, it's called Cauchy's integral theorem. And this is what you use when you're integrating around a closed loop. So, Cauchy's integral theorem. Now here, I should mention something. In William Chen notes, and also in the notes I put up a few weeks ago, Cauchy's integral theorem is stated for what's called a star domain. Whereas what G has done in lectures, he's stated the theorem for what's called a simply connected domain. So the version which G has proved it in, it's much stronger than a star domain, because every star domain is simply connected anyway. Whereas the converse is not necessarily true. So I don't think it's even appropriate I go into what it means to be a star domain, because now that you know it for simply connected domains, you can just use the result G has proven. So, Cauchy's integral theorem, it has two ingredients. So if you have a simply connected domain D, and a function f which is analytic in D. So those are the two ingredients. I should mention what does simply connected mean. Actually, it's something which to state formally, it's a bit beyond Math 236. I think for the formal definition of simply connected, if you continue to study maths, maybe you'll see it in third here. For now, the best way to think of it, it's just a simply connected domain is a domain with no holes, basically. So I'll write that down. Simply connected equals domain with no holes. So maybe something like this. Yep, so this one here. This would be a simply connected domain, because as you can see, it has no holes in it. But if I draw something like this, right, then this one here is obviously not simply connected. So I think that's the best way to think of it for now. A simply connected domain is a domain with no holes. Anyway, back to the theorem. If you have a simply connected domain D, and you have a function f which is analytic in D, then Cauchy's integral theorem says the following. It actually tells you two things. The first thing it tells you is that f has an analytic antiderivative in D. So and again, I'll call the antiderivative capital F in D. So that's the first conclusion of the theorem. The second conclusion, which is the main conclusion, and a conclusion which usually people are referring to when they mention Cauchy's integral theorem, is that the integral along C of the function f is equal to 0 for any closed contour C in D, right? So if you have a simply connected domain, and within that domain you draw some closed contour, something going in a loop, then the integral of f along that closed contour will be 0. So let me give you an example of how this theorem works. So consider the following example. Let's say I wanted to compute the integral of sine z dz along some closed contour C. And I'll draw C to be anything actually, so let's say this is the complex plane, and let's say C is the following curve. Something completely random. Okay? Something like that. So you can see the nice thing about this theorem is I don't even need to know what C is. What I can say that we can contain C inside a simply connected domain D. Alright, that part is fairly straightforward. I can just draw some simply connected domain which contains C. As you can see, that domain D which I've drawn, it doesn't have any holes in it, right? So it's simply connected. Now, the next thing I say is that, well, since the function sine z is entire, remember, what does entire mean? Entire means that it's analytic everywhere. So that's a well-known fact that sine z, cos z, the exponential function, for instance, these are all entire functions. They're analytic everywhere, and you can just state that. Anyway, since sine z is entire, because it's analytic everywhere, of course it's going to be analytic within D as well. So sine z will be analytic in D. So I have both ingredients necessary for Cauchy's integral theorem. I have a simply connected domain D, I have a closed contour lying in D, and I have a function sine z that's analytic within D. So I can apply Cauchy's integral theorem, which in this case tells me that the integral along C of sine z dz equals 0 by Cauchy's integral theorem. Now, you may be thinking, what exactly is the power of this theorem? Because I could have just answered this question using the fundamental theorem, actually, right? If we go back to the fundamental theorem for just a second, remember that, what does it say? It says you calculate the antiderivative at the endpoints, and then you subtract. So, according to that theorem, if you're integrating around a closed loop, obviously your endpoints are going to be the same, right? Z1 and Z2 are going to be the same. So, of course, that integral is going to be 0. If you wanted to do it in the case of this example, what you could do, you could take some point on C, I'll call it Z star. Then I could say, as an alternative solution, I could say, since sine Z has antiderivative minus cos Z, which is analytic in D, then by the fundamental theorem, integral of sine Z dz. Now I can treat Z star, because C is a closed loop, I can treat Z star as being the initial point and the terminal point of C, because it's a closed loop. So I can think of the integral along C as being the integral along Z star to Z star. Right? So according to the fundamental theorem, I'm going to get this guy going from Z star to Z star, and that's obviously going to be 0. So I could have answered that question using the fundamental theorem, and so when I do this, you may be wondering, what's the point of Cauchy's integral theorem? Can't we just do the same thing using the fundamental theorem? The answer is, in this case, yeah, it's not the Cauchy's integral theorem isn't of much use, but sometimes you'll get a problem where you're integrating a function around a closed loop. It's clear that the function is analytic, but it's very hard to actually compute the antiderivative of your function. So let me give you another example to demonstrate what I mean. So let's say, for instance, we want to calculate the following. Compute the integral along C of e to the z squared dz. And again, I'm just going to take C to be some random closed contour in the complex plane. So maybe something like this. Okay. Now here, in this case, I can't really use the fundamental theorem. Why? Because I don't really know how to integrate e to the power of z squared, right? This is actually a special function. It's not so much that e to the z squared doesn't have an antiderivative, but it's well known that you can't express its antiderivative in a simple way. So I can't really use the fundamental theorem. And this is where Cauchy's integral theorem would come into play. So what I do is I draw some simply connected domain D containing C. Like this. So when you're writing down your solution, you should write something like we can contain C inside a simply connected domain D. Right? Now, e to the z squared is entire, right? Obviously it's analytic everywhere, so it's going to be analytic in D as well. So, since e to the z squared is entire, it is analytic in D as well. So it follows from Cauchy's integral theorem that this integral is just going to be 0. Cauchy's integral theorem, right? And interestingly, remember Cauchy's integral theorem tells you two things. Not only is this integral 0, but Cauchy's integral theorem also guarantees that e to the z squared will have an analytic antiderivative in the region D. And like I said, this is something that is well known. It's well known that this function does have an antiderivative. It just can't be expressed in terms of your everyday functions. So that's an example of a case where you can't really use the fundamental theorem because you can't find the antiderivative. So instead you will use Cauchy's integral theorem. I'll give you another example which is similar, the same spirit, but maybe a little bit trickier. Let's see. Okay, how about this one? Compute the integral along C of log, the principal log function, because notice I'm writing it with a capital L, of z minus I dz, where I'll take C to be the following. Okay, so modulus of z minus 3 is equal to 1. Remember what that represents a circle centered at the point 3 with radius 1. So what does it look like? Looks like this. So you have circle there. So let's say this is the point 3. Oops. Fix that. Say this is the point 3. So that'll be the point 4. That will be the point 2. So it's a circle centered at 3 with radius 1. Now the question doesn't tell us in what direction the circle is going. And that happens quite often actually. Often the question won't say. When it doesn't say, you always assume it's going anti-clockwise. So, like that. Okay, so we want to integrate log of z minus I around C. Now, again, I could use the fundamental theorem, but again, it's hard to integrate the log function. So I go for Cauchy's integral theorem. Now, Cauchy's integral theorem requires me to work in a simply connected domain D, where my function is analytic. And this is where I have to be a bit careful. Remember the log function by itself, the principal log function, is analytic everywhere except for the negative real axis. So there basically. Log z, oops, sorry about that. So log z is analytic everywhere except for that pink line. Okay, so that's log z, but what about log z minus I? Well, if log of z is analytic everywhere except for the pink line, log of z minus I will be analytic everywhere except for basically that line shifted up by 1 unit. So what I mean is, that line there, so this one here, I. If you think about it, if you take any point on that green line and you subtract I, you'll get to the pink line. So log of z minus I, log of z minus I will be analytic everywhere except for the green line. Will be analytic everywhere except for the green line. So, what do I gotta do? I gotta draw a simply connected domain D that contains C but avoids that green line basically. And that's easy enough. I can just draw something like this. And I can call that D. Then notice that the domain D that I've drawn, it doesn't have any holes, so it's simply connected. And it avoids the green line, so my function is going to be analytic inside D. And so both conditions for Cauchy's integral theorem will hold. So D is a simply connected domain. That's the first thing. And the second thing is log of z minus I is analytic in D. So I can apply Cauchy's integral theorem and conclude that the integral along C of log z minus I dz is equal to 0 by Cauchy's integral theorem. Like that. So hopefully now you have a bit of a you have a good idea of how Cauchy's integral theorem works. It's not really a complicated theorem. If you have a closed contour and your contour lies in a domain where your function is analytic, it just says the integral is 0. Nothing too complicated.